Okay, so here's a quick reminder about vectors. Firstly, I apologise for my grubby fingernails. I've been out playing with my bike. So when we're working in 2 dimensions, the vector 2, 3 is 2 units in the x direction, 3 units in the y direction. It can also be written like this. I is a unit vector in the x direction, so it's a journey of 1 unit in that direction, and j is a unit vector in the y direction. And you may remember that whenever I see vectors written like this, I immediately write them in column form because I just find it a whole lot easier. And because it's a journey like this, we can work out its length, which we signify like that using Pythagoras. So when we move to 3 dimensions, we introduce a third axis, and the way it's normally represented is we sort of fold our xy axes flat on the page, and you've got your third dimension, which we call the z-axis, coming out of the page. You don't have to worry about it. You'd never be expected to draw an accurate picture of a 3D vector. So here's a 3-dimensional vector. It's a journey of 2 units in the x direction, 5 units in the y direction, and then 4 units up out of the page. Using the unit vector notation, that is 2i plus 5j plus 4k, k being a unit vector of 1 unit in the z direction. And as I said before, if ever I see a vector written like this, and they normally are in questions, I immediately change them into column form because I find that a whole lot easier. And you may remember that to work out the length of this vector, we still use the 3-dimensional version of Pythagoras, so it is this, and it is still the square root. It's not the cube root, it's the square root of the 3 dimensions squared. If you remember back to GCSE, it was this was the shortcut we could use to work out the longest length inside a box. Okay, so this vector here, which is described with a small letter, normally in bold, just describes a journey of 2 units in the x, 5 units in the y, 4 units in the z direction. That's just a journey. It's not fixed in space. It could be any journey of that with those dimensions. This vector is describing the journey between 2 fixed points. So it's between a point A and a point B. And this vector is described as a position vector because it describes how you get to point B from the origin, from your starting point. And you can choose to write this as a 3-dimensional coordinate if you like. So this describes the journey to get to this point here. So let's consider 2 position vectors, OB and OA. And let's say we want to work out how do I get from A to B. So it's not this. That was just an example. So we're now looking at these 2 vectors. So I'm going to draw a diagram, and I'm not in any way going to attempt to make that diagram accurate. I'm not going to try and work out what this would look like and what this would look like. I'm just going to say, okay, there's my origin. A comes before B in the alphabet, so I'll do A here and B here. Okay, so there's no indication that that's in 3D space, doesn't matter at all. So this vector here is the journey 1, 2, minus 3, and this vector here is the journey 2, 5, 4, and I want to know what the journey from A to B is. And it's important to remember that the direction is important, so the journey from A to B will not be the same as the journey from B to A, although you'll remember that they are very closely related. So if I want to get from A to B, the only way I can do it is to use the roads that I already know. So I know this road here, and I know this road here. So you may remember that we say to get from A to B, we go backwards along this road. So we go -1, -2, and +3, and then forwards along this road. So the x value is going to be -1 plus 2. The y value is -2 plus 5, and the z value is -3, so that's 3 plus 4. The other way to think about it is, what's the gap between that number and that number? What's the gap between that number and that number? What's the gap between that number and that number? Okay, so now I just want to talk about vectors being parallel. So let's take a vector so that's a journey of 1 unit in the x direction, 2 units in the y direction, and then 5 units in the z direction. Any vector where all 3 of those get multiplied by the same number will be parallel to that vector. So for example, this vector here, those two are parallel because there's a multiplier of 3, and that works for all 3 of the values. However, this vector is not parallel to this one, because although the first two numbers have multiplied by 4, the third number has not. So this one is parallel, that one is not parallel. So here's a question, and I've got to show these two vectors are not parallel. So firstly, they're written in unit vector form. I perhaps didn't make that clear enough here. We call this unit vector form. I, j and k are referred to as unit vectors, and the length of one I is 1. I is a vector of one unit in the x direction, and the length of j is 1, and the length of k is 1. Anyway, let's return to the question. So the first thing I'm obviously going to do, as I always say I'm going to do, is I'm going to turn these into column vectors. I find them so much easier. So that's 3/4, that's 1/3, and that's -2. And b is so I'm going to look at the multiplier. Going from here to here, it's been multiplied by 1/3, it's divided by 3. But going from here to here, it's been multiplied by 3. So clearly the same multiplier isn't being used. It doesn't matter what's going on here. I mean, this one's been multiplied by 1/3 again, but because all 3 components haven't been multiplied by the same thing, they are not parallel. So how would I write this? I would say that 3, no, I wouldn't say that. I would just probably do little arrows like this and show, say, because the same multiplier isn't used in each case, they're not parallel. So here's a development of the parallel argument. We're being asked to show these 3 points are collinear. Collinear means in a straight line. And to do this, we're going to work out the vector from A to B. We're going to work out the vector from B to C. We're hopefully going to show that they are parallel using the thing we just talked about, but we're also going to be able to say that they share a point. So if they're going in the same direction and they go through the same point, they must be in a straight line. So probably don't need a diagram, but I'm going to do one. I like a picture. So again, no attempt whatsoever to try and make these accurate. I'm just saying, right, A, B, C, there we are, and I'm going to straight away write them as column vectors. So O to A is 2, -1, 1. If there's a letter missing, so if it was 2i plus k, you'd have to remember to put a 0 in. So yeah, make sure you don't get caught out by one of those. This is 1, 2, 3, O to B, 1, 2, 3, and O to C is -1, 8, 7. So the vector from A to B, using the technique we said earlier, so that's backwards along here and up there, so it's -2 plus 1, and it's -1 plus 2, and it's -1 plus 3, or again it's just the jump. So that's A to B, and B to C using a similar technique, so -1 and -1, so that's -2, that's 6, and that's 4. So I can, So I can see that to get from AB to BC, we're doubling everything. So I can write BC equals 2AB. So they are parallel. But they also share a point. Therefore, they are collinear. So here's some practice from the new CGP book. This is the CGP Pure book, vectors features in both pure and mechanics. Just a point, they often use 3D coordinates. So if they say that there's a point C with the coordinates -1, 3, -5, that means that the vector OC is -1, 3, -5, or it could be written as -I plus 3j minus 5k. So have a go at those and drop me an email to tell me how you got on. So mcooper@ilfracombeacademy.org.uk.